Hi everyone. Here we are again with another video I decided to record um, based on the positive feedback I received from many of you. Um, I think the difference with this video is my intent is to try to um, cover some of the basics um, from my point of view when people looked into embarking on a preamp design and build for their audio amplifiers or the audio systems. And it might be not a useful video for experienced and builders. So who knows? You might even get something out of this. You will tell me. I would really love to hear your comments and thoughts. If you can comment in the YouTube comment section, that would be much appreciated. So I know what to change, what to focus, what you would like me to address differently, or anything else. Um, right. Without further ado, let me crack on with today's session. It's not rehearsed, so hopefully I'm not rambling too much, and I get to the bottom of things with enough level of detail and depth that you're expecting. Um, so today I'm covering the 112a preamp. I haven't mentioned it that much. I thought it was a good one to start with. Might not be a lot of controversy about the valve and not much experience out there. So if you do, please let me know. But I will share what I've done over the years. So let me get started with right. So the agenda for the video is I'll do some sort of an introduction. There's 4 points, right? I want to cover the introduction on why we decided to work with DHT. Why do I need a preamp? Why the 112A? And then I'll show 2 different approaches to build a preamp: the traditional transformer coupled and an unorthodox solution, which you might really guess what I'm going to talk about. But I'm not saying one is better than the other. I love both of them. I have built both of them and I use them extensively in my systems. But I decided to take a path of working with hybrid mu follower topology quite a lot, and that's what you're going to see where I spend most of my designs and some of the testing I'm doing. Okay, so let's get started with the introduction. Um, First of all, is do you need a preamp? Uh, I do get tons of emails asking. You wouldn't believe all sort of questions about this. How do I make my system sound more clear, or how do I get to um, get a better expression on the instruments? And unfortunately, there is an answer well known in the consulting world, which is it depends, and it's more applicable than ever in this context. You need to answer yourself the question first of what is missing in your current system in order to come to a conclusion that you need a preamp, and then what type of preamp you need. You might notice that you don't have enough gain, you don't have good dynamics. You might be aware that your amplifier, as a solid state one, has a lower impedance, input impedance like 10K or lower, and your source cannot handle that effectively. But the reality is, the majority of modern equipment, it is designed to have sensitivity to handle the typical source levels. Of course, if you have a valve amplifier, you might not have the same levels of sensitivity and gain, and that's where you might want to explore having a preamp either as a buffer because you need some current drive impedance matching, or as a voltage gain stage because you need more voltage level in your amplifier. Those two options can lead you to different topologies, different valves, and different results. Plugging in the wrong, plugging in a preamp in the wrong amplifier, in the wrong setup might lead to the wrong results. I have heard a lot of people designing and building preamps, and then complaining, "Oh, there is a lot of noise. There's a too much gain in the system," and in many cases, the answer to those questions or those statements is you've got the wrong preamp in your system. So the second point is why DHT, and I'm not going to deep dive on this because in hi-fi, like everywhere else, there is a lot of opinions, and I don't want this to turn into an opinion-based discussion. There is clearly DHTs, the directly heated triodes, are very linear devices, and they are thought to be used in output stages like 300Bs, 245s, 211 A45s, the classic 45, 2A3s. There's 50s, which are very rare and difficult to get to. And all the new incarnations being done gratefully by Elrock, for example, that can give you DHTs, but that doesn't mean that indirectly heated triodes or pentodes are bad. They are super good as well, but I like to, as many other people, I like to use the right valve for the right role. I wouldn't put a DHT on a phono stage, on an input stage, for example, but yes, they do play a great role in a preamp as well as an output stage. So I'm not going to get into this, but if you have made the decision that you want to experiment with DHTs in your system, then this is the route you want to take. Selecting the valve is it's important. There are many valves out there. Let me kind of give a couple of examples. So a very famous and lovely valve is a 26. You can see the data sheet here. There are other ones like the 112a, which I'm gonna cover today, as well as my favorite one, which is the 01a. They all have different characteristics, and the data sheets, unfortunately, they do not tell you how this sound, and that's the beauty of this hobby. It's important to see what other people and hear their experiences and try to replicate and judge yourself what you prefer in your system. That's about your decision and your conclusion. But anyhow, you would ask yourself the question easily if you have some technical background, thinking, okay, why would I choose an 01A which has a significantly higher anode or plate resistance and lower mutual conductance compared to the one you were talking about, like a 112A, which has significantly better parameters compared to that, and of course compared to more modern valves, not good examples, not the best. But the reality is these data sheets and these parameters do not tell you the complete truth on how they actually sound when you put them in a preamp. Anyhow, let's get back to where we were. And yeah, once you decide which valve you want to use, and again, depends on the gain requirements, it depends on your feedback of what you have heard from other people's systems, or or what you have at hand as well. Um, you shouldn't underestimate one of the most important topics, which is the power supply. The power supplies are where all most of the money goes. Don't make a decision of selecting a valve based on cost, because you might make the wrong decision, because the majority of the budget will go into the iron in your system, either the interstage transformers, output transformers, or the all the chokes and transformers you have in the filament supplies and the HT supply. I'm not going to cover in this video. The power supply is a huge topic, very important one. There is a lot of material out there you can read. I'm not going to cover that, but I suggest you pay attention to this important aspect of the amplifier. Right, so let me kill the camera here, and yeah, so the 112a, I've got my first pair of this amazing tube many years ago when I lived in Argentina. I think it was a lovely pair of RCA Cunningham, like the one show in the picture on the left from Thomas Meyer in his blog, which I recommend you pay a visit, because he has a fantastic material there to look into. I have a pair of that initial pair, and I decided to use them as preamp, and I was very impressed with the results. And I think one of the reasons is that you can drive them at a fairly good current with a lower anode resistance compared to other DHTs. And it has a very gentle requirement, like O1A in terms of the filament, although is an oxide coated one, which was an advanced in the technology developed in order to get a better performance on the tubes overall. Anyway, I'm sure there's some old chaps out there that can older than me, that they can shed some light on the history, and they are quite more knowledgeable on the tube itself. But yeah, as I show before, if we look back again into the data sheet, sorry, this is the one. You'll see these are typically the curves you get on the data sheet, and they might not be the best ones, but what was produced with the technology at the time, that might not tell you how linear the curves are, although you can see even spacing between the curves. That is what you're looking for, and they're not all the time you get curves like the one here on the right, where you can see, you can see the transfer curve between the grid and the plate, and that will tell you where to bias the stage to a degree, because you want to operate on the most linear side of the tube, which is where you have a linear line here, not the curve on the bottom. So look at where the 8 milliamps point is. That sounds like a very nice point to bias the tube, which is obviously then proved with the results we're gonna cover later on. At the time, you look at these curves, and they're not the best ones to help you to design which point you want to select. So I got very into curve tracing, into developing my own curves. I developed my own curve tracer many years ago, nearly 20 years ago, and I loved and I used it for many years. Then I got into the e-tracer and mu tracer as develop a solid state software base, which are much more advanced, and you can get plenty of additional things. As an example, I kind of end up developing my own LT-Spice models, which are very useful for simulating your designs, and I've been sharing these models with the world, and people have used them extensively. So it's a very useful tool for developing, and actually helps you with in the learning process. So yeah, it's, you can see with the curves, it's a very linear tube that it's a sign that it could be a good candidate for a preamp, but the judge is your ears in the end. So right, so what is the traditional approach? You can see here we have, a classic DHT with a filament regulator and filament bias, and we have a transformer load here, and you would say, oh great, I don't have a capacitor in the signal path. The answer is incorrect, because the capacitor still is on the power supply is well in the signal path, and because of the lower the lower supply rejection that this topology has, you have some disadvantages, and the power supply on the HT side plays a bigger role than other topologies. But again, this is a very simple solution. You are at the mercy, or you need to spend as much money as you can on the transformer, because the quality of the transformer will dictate significantly how well the stage sounds. So this is what I designed back in the days, and I had a revisiting, I think 2017 version was using elements of this. But anyhow, the initial 112a preamp that I unfortunately don't have some full measures of this, but it was running with the Lundell LL2745 gap to 8 milliamps. I use this transformer quite a lot with different stages on 1A, which is got quite famous, and a step down a ratio of 5.6 to 1. What does it mean? That it's that the transformer is reducing the voltage by 5.6, but also it's lowering the impedance and multiplying at the same time the output current capability. So this stage, for example, with a transformer like that, will have a very low gain, like 1.5, despite of the gain of over 8 of the amplification factor of the tube. That's then the gain that the tube brings, then it's reduced by the transformer by 5.6. That's how you get to 1.5. But the other benefit is that 8 milliamp current drive that has in the primary is reflected in the secondary as a very like more over 30 milliamps, I believe, if you do the math on the transformer. And equally, the output impedance is reduced significantly to 400 ohms-ish level, if my memory doesn't fail me. If you take into account the impedance transformation of the transformer, but also you have to take into account the output resistance of the plate resistance of the valve, as well as the primary resistance of the transformer, which is 1.3K, which is not minimum, but it's considerable into the equation. And also you need to reflect in the anode the filament resistor, which is unbypassed, but is low enough that doesn't make any any bad contribution. The performance of this stage is pretty good. You get good flat response up until 30 kilohertz from 5 hertz, I believe, or so. So it's really good, very simple to design and build. You have some drawbacks, which is, as I mentioned, the supply noise. It's more evident because the power supply noise rejection is low, given that the transformer is the only element isolating the anode to the power supply. And then, of course, as usual in the DHTs, you have the filament, which is super critical that you have the best solution. Currently, here you have rod column and filament regulator to manage this. I've done, I think it's incorrect, some of the data should be the filament resistor. If you I think I've used it with starvation, which is not good for oxide filaments, as everyone knows. But I think I've starved it from 250 milliamps down to 200 milliamps, which obviously gives lower distortion and lower microphonic noise. But I think the filament resistor goes into 25 ohms instead of 20. But that's something you can, I think I'm showing in a different diagram. Yeah, the other end, if there is no starvation, the other end of the filament, instead of being 8 volts, should be 10, because it's a 5 volt filament tube. Anyway, the other, it's a very good bandwidth, not the best, but the other limitation here is the loading effect. Whatever you put on the secondary will be reflected, and that has an impact on the overall performance of the amplifier in terms of distortion, etc. Yeah, a great benefit that I missed out listing here is the galvanic isolation. Note that the secondary is not grounded. You can ground it if you want to, and in practice I ended up having like a switch to ground depending on what grounding scheme I have on the amplifier. But this is a fantastic benefit that the transformer brings. You don't need to ground. You kind of get a differential signal, which is quite useful in the depending on your overall amplifier topology and system. So yeah. My kind of unconventional solution, it's the hybrid mu follower one, and this is what I revisited in 2017, I believe, and I have an example in a minute, which again the same I think is the same mistake here about the filament voltage. Here the example is without starvation, so it should be 10 volts at that end, because it's 5 plus 5 of the filament is 10, not the 8 that is written on the diagram, so ignore that. Sorry, my mistake here. But yeah, the benefits, as I mentioned in the website, is you have wider bandwidth, all the way from 3 hertz to 700 kilohertz here, goes into megahertz stage. This is great because on one hand it gives you better treble. People normally will react to it instantly, perceiving better results on the treble, on the instruments, on the high frequency elements. But it's a double-edged sword, because at the same time, it does. If the stage has a lot of gain, it's a high bandwidth amplifier, and noises that you would normally not hear, can create an issue in your amplifier. And I've seen people using this stage, as I do in my 300B amp, where I have a D3A driver using this same topology, and is a very high bandwidth, high gain amplifier, and that can create a lot of problems in your system if you don't take the right measures. Anyway, this stage has no transformer. You have basically the hybrid mu follower board. You have a coupling capacitor that, yes, you have one cap in the signal path there, and the rest of the circuit is the same. You can play with different voltage supplies. Again, this 125 is a mistake I left from the previous slide, but the right example is on the following slide, so bear with me. You have, what are the benefits? You have a wider bandwidth, as I said. You have higher power supply rejection, which means you have more isolation with the HT power supply, which in result means that you can be a bit more flexible with the HT. If you use different rectifiers, you might not notice the same difference because there is a lot of isolation. You have higher gain because the gain of the stage, you cannot control it, is dictated by the mu of the valve, which is good and can be bad because you can end up with too much gain for your system. That opens up another question and another solution. How do we lower the gain? But definitely, because of the way this stage works, there is lower distortion. The hybrid mu follower acts as a impedance multiplier, so the valve is actually operated with a load that ideally is much bigger than the load that you're actually presenting to the preamp, and that takes the valve to operate as linear as much linear as it can be. So also the output impedance is the lowest because the output impedance is the inverse of the transconductance of the MOSFET that it's on the top element of the hybrid mu follower, and which is on the order below 50 ohms. And you have some current drive that it's not just sinking the 8 milliamps that the valve is sinking, but also it can source as much current that is needed. This is great for supporting the right slew rate of and the dynamics of the amp. Having good current, sufficient current, is crucial in any stage to ensure that the stage responds well to dynamics. And the result, you might not be able to measure it easily, but you can hear it, and that's what we are all into this. Filament resistor, they're very tricky ones. You need, I think Andy Evans have covered this extensively with his experiments. They are very specific type of resistors. We ended up using wire one types because anything you put in the filament, in the cathode, is super critical because it affects the sound massively. That's why we have the rod Coleman filaments, but also you can have SiC diodes, silicon carbide diodes, which are used as well in many cases, or a filament resistor there. So now moving forward, okay, so this is what I did back in 2017. This is a picture of the preamp showed at the beginning of this video, and this is the circuit. It is available on the blog. You want to explore it. All of these elements here are part of the PCBs. It makes it easier to build. I currently do not use the BF862 because it's end of life, but there are some other great alternatives which I have commented before. Yeah, and a Teflon output capacitor and another Russian film capacitor as part of the hybrid move follower board. But all of these components except the capacitor are part of the board. Also this kind of external bias, grounding bias resistor, the R8 at the output, and of course, as I've shown before, this is a starved stage where I lower the bias to 200 milliamps. It didn't really kill the valve. Of course, the life expectancy gets reduced, but that's not something I was truly worried. If you feel uncomfortable, you can pump it up to 250 milliamps, and it should be, and the filament resistor should be 20 ohms instead of 25. But yeah, so that's what I've done. It sounded amazing, very simple and easy stage to build. You can have a different ground lift if required, a switch or not, that's your own choice. How does it measure? And this is an interesting aspect to highlight. I often have published as much as I could these diagrams. They do tell some interesting stuff, but they do not tell the full story. It's important to do take these measures if you can, because when they do look bad, they are obviously a sign that things are not good in your system. But here is a good example that is worth highlighting. It's a 4 RMS volts output, so it's at full tilt. I would normally use this potentially. You have quite a low distortion. It's 0.0316%. It's really low, and but more importantly, on the distortion is the harmonic profile. You can see the second harmonic and the fourth are kind of even harmonic, are more present than the third. You know, it's still not that visible here. And mind you that we're talking about 90 dB signal to noise ratio, so it's pretty quiet. There is no signs of intermodulation. Distortion here is very low, and the the byproducts of the filament supply are very, very low, thanks to the to the rod Coleman filaments regulators. So yeah, here is, I'm flicking quickly. When you push it to 10 volts RMS, you can see how the different harmonics start to creep up. You can see here we've got the you can see where the odd harmonics started to become more predominant, but still the progression and the decay is quite natural, and that reflects a very good performance and of this valve in my experience. So yeah, finally, I hope you enjoy this. It's another over half an hour of rambling, but I hope this is giving you a good idea of what to look and what to take into account when you design a DHT preamp. There are some examples I've touched on, some of the different tubes, different topologies. I love both of them. They are producing amazing results, both of them. I'm going to link below the different blog post entries which have much more information and detail if you are interested in building any of these preamps. But so anyway, I hope this was good for you. If you have any feedback, please do share, because that will help me to improve how do I record these videos and what do I cover for future. So, okay, see you next time. Thank you. Bye.